Game theory is a study of strategic decision-making. Specifically, it is the study of mathematical models of conflict and cooperation between intelligent rational decision-makers. An alternative term suggested as a more descriptive name for the discipline is interactive decision theory. Game theory is mainly used in economics, political science, and psychology, as well as logic, computer science, and biology. The subject first addressed zero-sum games, such that one person's gains exactly equal net losses of the other participant or participants. Today, however, game theory applies to a wide range of behavioral relations, and has developed into an umbrella term for the logical side of decision science, including both humans and non-humans. Modern game theory began with the idea regarding the existence of mixed strategy equilibria in two-person zero-sum games and its proof by John von Neumann. Von Neumann's original proof used Brouwer fixed-point theorem on continuous mappings into compact convex sets, which became a standard method in game theory and mathematical economics. His paper was followed by the 1944 book Theory of Games and Economic Behavior, co-written with Oskar Morgenstern, which considered cooperative games of several players. The second edition of this book provided an axiomatic theory of expected utility, which allowed mathematical statisticians and economists to treat decision-making under uncertainty. This theory was developed extensively in the 1950s by many scholars. Game theory was later explicitly applied to biology in the 1970s, although similar developments go back at least as far as the 1930s. Game theory has been widely recognized as an important tool in many fields. 10 game theorists have won the Nobel Memorial Prize in Economic Sciences, and John Maynard Smith was awarded the Crawford Prize for his application of game theory to biology. Representation of games. The games studied in game theory are well-defined mathematical objects. To be fully defined, a game must specify the following elements: the players of the game, the information and actions available to each player at each decision point, and the payoffs for each outcome. A game theorist typically uses these elements, along with the solution concept of their choosing, to deduce a set of equilibrium strategies for each player such that, when these strategies are employed, no player can profit by unilaterally deviating from their strategy. These equilibrium strategies determine an equilibrium to the game, a stable state in which either one outcome occurs or a set of outcomes occur with known probability. Most cooperative games are presented in the characteristic function form, while the extensive and the normal forms are used to define non-cooperative games. Extensive form. The extensive form can be used to formalize games with a time sequencing of moves. Games here are played on trees. Here each vertex represents a point of choice for a player. The player is specified by a number listed by the vertex. The lines out of the vertex represent a possible action for that player. The payoffs are specified at the bottom of the tree. The extensive form can be viewed as a multiplayer generalization of a decision tree. In the game pictured to the left, there are two players. Player 1 moves first and chooses either F or U. Player 2 sees Player 1's move and then chooses A, or suppose that Player 1 chooses U and then Player 2 chooses A, then Player 1 gets 8 and Player 2 gets 2. The extensive form can also capture simultaneous move games and games with imperfect information. To represent it, either a dotted line connects different vertices to represent them as being part of the same information set, or a closed line is drawn around them. Normal form. The normal game is usually represented by a matrix which shows the players, strategies, and payoffs. More generally, it can be represented by any function that associates a payoff for each player with every possible combination of actions. In the accompanying example, there are two players. One chooses the row and the other chooses the column. Each player has two strategies, which are specified by the number of rows and the number of columns. The payoffs are provided in the interior. The first number is the payoff received by the row player. The second is the payoff for the column player. Suppose that Player 1 plays up and that Player 2 plays left. Then Player 1 gets a payoff of 4, and Player 2 gets 3. When a game is presented in normal form, it is presumed that each player acts simultaneously or, at least, without knowing the actions of the other. If players have some information about the choices of other players, the game is usually presented in extensive form. Every extensive form game has an equivalent normal form game, however the transformation to normal form may result in an exponential blow-up in the size of the representation, making it computationally impractical. Leighton Brown and Chuan 2008, PA 35, Characteristic Function Form. In games that possess removable utility, separate rewards are not given. Rather, the characteristic function decides the payoff of each unity. The idea is that the unity that is empty, so to speak, does not receive a reward at all. The origin of this form is to be found in John von Neumann in Oskar Morgenstern's book. When looking at these instances, they guessed that when a union appears, it works against the fraction as if two individuals were playing a normal game. The balanced payoff of C is a basic function. Although there are differing examples that help determine coalitional amounts from normal games, not all appear that in their function form can be derived from such. Formally, a characteristic function is seen as, where n represents the group of people and is a normal utility. Such characteristic functions have expanded to describe games where there is no removable utility. General and applied uses. As a method of applied mathematics, game theory has been used to study a wide variety of human and animal behaviors. It was initially developed in economics to understand a large collection of economic behaviors, including behaviors of firms, markets, and consumers. The first use of game-theoretic analysis was by Antoine-Augustin Cournot in 1838 with his solution of the Cournot duopoly. The use of game theory in the social sciences has expanded, and game theory has been applied to political, sociological, and psychological behaviors as well. Although pre-20th century naturalists such as Charles Darwin made game-theoretic kinds of statements, the use of game-theoretic analysis in biology began with Ronald Fisher's studies of animal behavior during the 1930s. This work predates the name game theory, but it shares many important features with this field. The developments in economics were later applied to biology largely by John Maynard Smith in his book Evolution and the Theory of Games. In addition to being used to describe, predict, and explain behavior, game theory has also been used to develop theories of ethical or normative behavior and to prescribe such behavior. In economics and philosophy, scholars have applied game theory to help in the understanding of good or proper behavior. Game-theoretic arguments of this type can be found as far back as Plato. Description and modeling. The first known use is to describe and model how human populations behave. Some scholars believe that by finding the equilibria of games they can predict how actual human populations will behave when confronted with situations analogous to the game being studied. This particular view of game theory has come under recent criticism. First, it is criticized because the assumptions made by game theorists are often violated. Game theorists may assume players always act in a way to directly maximize their wins, but in practice, human behavior often deviates from this model. Explanations of this phenomenon are many. Irrationality, new models of deliberation, or even different motives. Game theorists respond by comparing their assumptions to those used in physics. Thus, while their assumptions do not always hold, they can treat game theory as a reasonable scientific ideal akin to the models used by physicists. However, in the centipede game, guess 2/3 of the average game, and the dictator game, people regularly do not play Nash equilibria. These experiments have demonstrated that individuals do not play equilibrium strategies. There is an ongoing debate regarding the importance of these experiments. Alternatively, some authors claim that Nash equilibria do not provide predictions for human populations, but rather provide an explanation for why populations that play Nash equilibria remain in that state. However, the question of how populations reach those points remains open. Some game theorists, following the work of John Maynard Smith and George R. Price, have turned to evolutionary game theory in order to resolve these issues. These models presume either no rationality or bounded rationality on the part of players. Despite the name, evolutionary game theory does not necessarily presume natural selection in the biological sense. Evolutionary game theory includes both biological as well as cultural evolution and also models of individual learning. Prescriptive or normative analysis, on the other hand, some scholars see game theory not as a predictive tool for the behavior of human beings, but as a suggestion for how people ought to behave. Since a strategy, corresponding to a Nash equilibrium of a game constitutes one's best response to the actions of the other players provided they are in Nash equilibrium playing a strategy that is part of a Nash equilibrium seems appropriate. However, the rationality of such a decision has been proved only for special cases. This normative use of game theory has also come under criticism. First, in some cases it is appropriate to play a non-equilibrium strategy if one expects others to play non-equilibrium strategies as well. For an example, see guess 2/3 of the average. Second, the prisoner's dilemma presents another potential counterexample. In the prisoner's dilemma, each player pursuing their own self-interest leads both players to be worse off than had they not pursued their own self-interests. Economics and business. Game theory is a major method used in mathematical economics and business for modeling competing behaviors of interacting agents. Applications include a wide array of economic phenomena and approaches, such as auctions, bargaining, mergers and acquisitions pricing, fair division, duopolies, oligopolies, social network formation, agent-based computational economics, general equilibrium, mechanism design, and voting systems. And across such broad areas as experimental economics, behavioral economics, information economics, industrial organization, and political economy. This research usually focuses on particular sets of strategies known as solution concepts, or equilibria based on what is required by norms of rationality. In non-cooperative games, the most famous of these is the Nash equilibrium. A set of strategies is a Nash equilibrium if each represents a best response to the other strategies. So, if all the players are playing the strategies in a Nash equilibrium, they have no unilateral incentive to deviate, since their strategy is the best they can do given what others are doing. The payoffs of the game are generally taken to represent the utility of individual players. Often in modeling situations the payoffs represent money, which presumably corresponds to an individual's utility. This assumption, however, can be faulty. A prototypical paper on game theory and economics begins by presenting a game that is an abstraction of a particular economics situation. One or more solution concepts are chosen, and the author demonstrates which strategy sets in the presented game are equilibria of the appropriate type. Naturally, one might wonder to what use this information should be put. Economists and business professors suggest two primary uses, descriptive and prescriptive. Political science. The application of game theory to political science is focused in the overlapping areas of fair division, political economy, public choice, or bargaining, positive political theory, and social choice theory. In each of these areas, researchers have developed game theoretic models in which the players are often voters, states, special interest groups, and politicians. Early examples of game theory applied to political science are provided by Anthony Downs. In his book An Economic Theory of Democracy, Downs 1957, he applies the hoteling firm location model to the political process. In the Downsian model, political candidates commit to ideologies on a one-dimensional policy space. Downs first shows how the political candidates will converge to the ideology preferred by the median voter if voters are fully informed, but then argues that voters choose to remain rationally ignorant, which allows for candidate divergence. It has also been proposed that game theory explains the stability of any form of political government. Taking the simplest case of a monarchy, for example, the king, being only one person, does not and cannot maintain his authority by personally exercising physical control over all or even any significant number of his subjects. Sovereign control is instead explained by the recognition by each citizen that all other citizens expect each other to view the king as the person whose orders will be followed. Coordinating communication among citizens to replace the sovereign is effectively barred, since conspiracy to replace the sovereign is generally punishable as a crime. Thus, in a process that can be modeled by variants of the prisoner's dilemma, During periods of stability, no citizen will find it rational to move to replace the sovereign, even if all the citizens know they would be better off if they were all to act collectively. A game-theoretic explanation for democratic peace is that public and open debate in democracies send clear and reliable information regarding their intentions to other states. In contrast, it is difficult to know the intentions of non-democratic leaders, what effect concessions will have, and if promises will be kept. Thus there will be mistrust and unwillingness to make concessions if at least one of the parties in a dispute is a non-democracy. Game theory could also help predict nations' responses when there is a new rule or law to be applied to that nation. One example would be Peter John Wood's research when he looked into what nations could do to help reduce climate change. Wood thought this could be accomplished by making treaties with other nations to reduce greenhouse gas emissions. However, he concluded that this idea could not work because it would create a prisoner's dilemma to the nations. Biology. Unlike those in economics, the payoffs for games in biology are often interpreted as corresponding to fitness. In addition, the focus has been less on equilibria that correspond to a notion of rationality and more on ones that would be maintained by evolutionary forces. The best-known equilibrium in biology is known as the evolutionarily stable strategy, first introduced in. Although its initial motivation did not involve any of the mental requirements of the Nash equilibrium, every ESS is a Nash equilibrium. In biology, game theory has been used to understand many different phenomena. It was first used to explain the evolution of the approximate 1:1 sex ratios, suggested that the 1:1 sex ratios are a result of evolutionary forces acting on individuals who could be seen as trying to maximize their number of grandchildren. Additionally, biologists have used evolutionary game theory and the ESS to explain the emergence of animal communication. The analysis of signaling games and other communication games has provided insight into the evolution of communication among animals. For example, the mobbing behavior of many species, in which a large number of prey animals attack a larger predator, seems to be an example of spontaneous emergent organization. Ants have also been shown to exhibit feed-forward behavior akin to fashion. Biologists have used the game of chicken to analyze fighting behavior and territoriality. According to Maynard Smith, in the preface to Evolution and the Theory of Games, paradoxically, it has turned out that game theory is more readily applied to biology than to the field of economic behavior for which it was originally designed. Evolutionary game theory has been used to explain many seemingly incongruous phenomena in nature. One such phenomenon is known as biological altruism. This is a situation in which an organism appears to act in a way that benefits other organisms and is detrimental to itself. This is distinct from traditional notions of altruism because such actions are not conscious, but appear to be evolutionary adaptations to increase overall fitness. Examples can be found in species ranging from vampire bats that regurgitate blood they have obtained from a night's hunting and give it to group members who have failed to feed, to worker bees that care for the queen bee for their entire lives and never mate, to vervet monkeys that warn group members of a predator's approach, even when it endangers that individual's chance of survival. All of these actions increase the overall fitness of a group, but occur at a cost to the individual. Evolutionary game theory explains this altruism with the idea of kin selection. Altruists discriminate between the individuals they help and favor relatives. Hamilton's rule explains the evolutionary reasoning behind this selection with the equation be aware the cost to the altruist must be less than the benefit to the recipient multiplied by the coefficient of relatedness. The more closely related two organisms are causes the incidences of altruism to increase because they share many of the same alleles. This means that the altruistic individual, by ensuring that the alleles of its close relative are passed on, can forego the option of having offspring itself because the same number of alleles are passed on. Helping a sibling, for example, has a coefficient of a 1/2, because an individual shares a 1/2 of the alleles in its sibling's offspring. Ensuring that enough of a sibling unregistered trademark S offspring survive to adulthood precludes the necessity of the altruistic individual producing offspring. The coefficient values depend heavily on the scope of the playing field. For example, if the choice of whom to favor includes all genetic living things, not just all relatives, we assume the discrepancy between all humans only accounts for approximately 1% of the diversity in the playing field. A coefficient that was a 1/2 in the smaller field becomes 0.995. Similarly, if it is considered that information other than that of a genetic nature persisted through time, the playing field becomes larger still, and the discrepancies smaller. Computer science and logic. Game theory has come to play an increasingly important role in logic and in computer science. Several logical theories have a basis in games semantics. In addition, computer scientists have used games to model interactive computations. Also, game theory provides a theoretical basis to the field of multi-agent systems. Separately, game theory has played a role in online algorithms. In particular, the K-server problem, which has in the past been referred to as games with moving costs and request-answer games. Yau's principle is a game-theoretic technique for proving lower bounds on the computational complexity of randomized algorithms, especially online algorithms. The emergence of the Internet has motivated the development of algorithms for finding equilibria in games, markets, computational auctions, peer-to-peer systems, and security and information markets. Algorithmic game theory and within it algorithmic mechanism design combine computational algorithm design and analysis of complex systems with economic theory. Philosophy. Game theory has been put to several uses in philosophy. Responding to two papers by W. V. O'Quinney, 1960, 1967, Lewis used game theory to develop a philosophical account of convention. In so doing, he provided the first analysis of common knowledge and employed it in analyzing play and coordination games. In addition, he first suggested that one can understand meaning in terms of signaling games. This later suggestion has been pursued by several philosophers since Lewis, Grimm, Kokalis, and Al-Itafdi A. 2004. Following Lewis' game-theoretic account of conventions, Edna Ullman Margalit and Bickery have developed theories of social norms that define them as Nash equilibria that result from transforming a mixed-motive game into a coordination game. Game theory has also challenged philosophers to think in terms of interactive epistemology, what it means for a collective to have common beliefs or knowledge, and what are the consequences of this knowledge for the social outcomes resulting from agents' interactions. Philosophers who have worked in this area include Bickery, Skymes, and Stalnaker. In ethics, some authors have attempted to pursue Thomas Hobbes' project of deriving morality from self-interest. Since games like The Prisoner's Dilemma present an apparent conflict between morality and self-interest, explaining why cooperation is required by self-interest is an important component of this project. This general strategy is a component of the general social contract view in political philosophy and Cava. Other authors have attempted to use evolutionary game theory in order to explain the emergence of human attitudes about morality and corresponding animal behaviors. These authors look at several games including The Prisoner's Dilemma, Stag Hunt, and the Nash bargaining game as providing an explanation for the emergence of attitudes about morality and Sober and Wilsoner, 1999. Some assumptions used in some parts of game theory have been challenged in philosophy. For example, psychological egoism states that rationality reduces to self-interest, a claim debated among philosophers. Types of games, cooperative/non-cooperative. A game is cooperative if the players are able to form binding commitments. For instance, the legal system requires them to adhere to their promises. In non-cooperative games, this is not possible. Often it is assumed that communication among players is allowed in cooperative games, but not in non-cooperative ones. However, this classification on two binary criteria has been questioned, and sometimes rejected. Of the two types of games, non-cooperative games are able to model situations to the finest details, producing accurate results. Cooperative games focus on the game at large. Considerable efforts have been made to link the two approaches. The so-called Nash program has already established many of the cooperative solutions as non-cooperative equilibria. Hybrid games contain cooperative and non-cooperative elements. For instance, coalitions of players are formed in a cooperative game, but these play in a non-cooperative fashion. Symmetric/asymmetric. A symmetric game is a game where the payoffs for playing a particular strategy depend only on the other strategies employed, not on who is playing them. If the identities of the players can be changed without changing the payoff to the strategies, then a game is symmetric. Many of the commonly studied two games are symmetric. The standard representations of Chicken, The Prisoner's Dilemma, and The Stag Hunt are all symmetric games. Some scholars would consider certain asymmetric games as examples of these games as well. However, the most common payoffs for each of these games are symmetric. Most commonly studied asymmetric games are games where there are not identical strategy sets for both players. For instance, the ultimatum game and similarly the dictator game have different strategies for each player. It is possible, however, for a game to have identical strategies for both players, yet be asymmetric. For example, the game pictured to the right is asymmetric despite having identical strategy sets for both players. Zero-sum/non-zero-sum. Zero-sum games are a special case of constant-sum games, in which choices by players can neither increase nor decrease the available resources. In zero-sum games the total benefit to all players in the game, for every combination of strategies, always adds to zero. Poker exemplifies a zero-sum game, because one wins exactly the amount one's opponents lose. Other zero-sum games include matching pennies and most classical board games including Go and chess. Many games studied by game theorists are non-zero-sum games, because the outcome has net results greater or less than zero. Informally, in non-zero-sum games, a gain by one player does not necessarily correspond with a loss by another. Constant-sum games correspond to activities like theft and gambling, but not to the fundamental economic situation in which there are potential gains from trade. It is possible to transform any game into a zero-sum game by adding a dummy player whose losses compensate the player's net winnings. Simultaneous/sequential. Simultaneous games are games where both players move simultaneously, or if they do not move simultaneously, the later players are unaware of the earlier player's actions. Sequential games are games where later players have some knowledge about earlier actions. This need not be perfect information about every action of earlier players. It might be very little knowledge. For instance, a player may know that an earlier player did not perform one particular action, while he does not know which of the other available actions the first player actually performed. The difference between simultaneous and sequential games is captured in the different representations discussed above. Often, normal form is used to represent simultaneous games, while extensive form is used to represent sequential ones. The transformation of extensive to normal form is one way, meaning that multiple extensive form games correspond to the same normal form. Consequently, notions of equilibrium for simultaneous games are insufficient for reasoning about sequential games. See subgame perfection. In short, the differences between sequential and simultaneous games are as follows: perfect information and imperfect information. An important subset of sequential games consists of games of perfect information. A game is one of perfect information if all players know the moves previously made by all other players. Thus, only sequential games can be games of perfect information because players in simultaneous games do not know the actions of the other players. Most games studied in game theory are imperfect information games. Interesting examples of perfect information games include the ultimatum game and centipede game. Recreational games of perfect information games include chess, Go and Mancala. Many card games are games of imperfect information, such as poker or contract bridge. Perfect information is often confused with complete information, which is a similar concept. Complete information requires that every player know the strategies and payoffs available to the other players but not necessarily the actions taken. Games of incomplete information can be reduced, however, to games of imperfect information by introducing moves by nature. Combinatorial games, games in which the difficulty of finding an optimal strategy stems from the multiplicity of possible moves, are called combinatorial games. Examples include chess and Go. Games that involve imperfect or incomplete information may also have a strong combinatorial character, for instance backgammon. There is no unified theory addressing combinatorial elements and games. There are, however, mathematical tools that can solve particular problems and answer general questions. Games of perfect information have been studied in combinatorial game theory, which has developed novel representations, for examples of real numbers, as well as combinatorial and algebraic proof methods to solve games of certain types, including loopy games that may result in infinitely long sequences of moves. These methods address games with higher combinatorial complexity than those usually considered in traditional game theory. A typical game that has been solved this way is hex. A related field of study, drawing from computational complexity theory, is game complexity, which is concerned with estimating the computational difficulty of finding optimal strategies. Research in artificial intelligence has addressed both perfect and imperfect information games that have very complex combinatorial structures for which no provable optimal strategies have been found. The practical solutions involve computational heuristics, like alpha-beta pruning or use of artificial neural networks trained by reinforcement learning, which make games more tractable in computing practice. Infinitely long games. Games, as studied by economists and real-world game players, are generally finished in finitely many moves. Pure mathematicians are not so constrained, and set theorists in particular study games that last for infinitely many moves, with the winner not known until after all those moves are completed. The focus of attention is usually not so much on what is the best way to play such a game, but simply on whether one or the other player has a winning strategy. The existence of such strategies, for cleverly designed games, has important consequences in descriptive set theory. Discrete and continuous games. Much of game theory is concerned with finite, discrete games, that have a finite number of players, moves, events, outcomes, etc. Many concepts can be extended, however. Continuous games allow players to choose a strategy from a continuous strategy set. For instance, corner competition is typically modeled with players' strategies being any non-negative quantities, including fractional quantities. Differential games such as the continuous pursuit and evasion game are continuous games where the evolution of the player's state variables is governed by differential equations. The problem of finding an optimal strategy in a differential game is closely related to the optimal control theory. In particular, there are two types of strategies. The open-loop strategies are found using the Pontryagin maximum principle while the closed-loop strategies are found using Bellman's dynamic programming method. A particular case of differential games are the games with a random time horizon. In such games, the terminal time is a random variable with a given probability distribution function. Therefore, the players maximize the mathematical expectation of the cost function. It was shown that the modified optimization problem can be reformulated as a discounted differential game over an infinite time interval. Many player and population games with an arbitrary, but finite, number of players are often called n-person games. Evolutionary game theory considers games involving a population of decision-makers, where the frequency with which a particular decision is made can change over time in response to the decisions made by all individuals in the population. In biology, this is intended to model evolution, where genetically programmed organisms pass along some of their strategy programming to their offspring. In economics, the same theory is intended to capture population changes because people play the game many times within their lifetime, and consciously switch strategies. Stochastic outcomes. Individual decision problems with stochastic outcomes are sometimes considered one-player games. These situations are not considered game theoretical by some authors. They may be modeled using similar tools within the related disciplines of decision theory, operations research, and areas of artificial intelligence, particularly AI planning and multi-agent system. Although these fields may have different motivators, the mathematics involved are substantially the same, for example using Markov decision processes. Stochastic outcomes can also be modeled in terms of game theory by adding a randomly acting player who makes chance moves. This player is not typically considered a third player in what is otherwise a two-player game, but merely serves to provide a roll of the dice where required by the game. For some problems, different approaches to modeling stochastic outcomes may lead to different solutions. For example, the difference in approach between MDPs and the minimax solution is that the latter considers the worst case over a set of adversarial moves, rather than reasoning in expectation about these moves given a fixed probability distribution. The minimax approach may be advantageous where stochastic models of uncertainty are not available, but may also be overestimating extremely unlikely events, dramatically swaying the strategy in such scenarios if it is assumed that an adversary can force such an event to happen. General models that include all elements of stochastic outcomes, adversaries, and partial or noisy observability have also been studied. The gold standard is considered to be partially observable stochastic game, but few realistic problems are computationally feasible in POSG representation. Metagames, these are games the play of which is the development of the rules for another game, the target or subject game. Metagames seek to maximize the utility value of the rule set developed. The theory of metagames is related to mechanism design theory. The term metagame analysis is also used to refer to a practical approach developed by Nigel Howard whereby a situation is framed as a strategic game in which stakeholders try to realize their objectives by means of the options available to them. Subsequent developments have led to the formulation of confrontation analysis. History. Early discussions of examples of two-person games occurred long before the rise of modern, mathematical game theory. The first known discussion of game theory occurred in a letter written by James Waldegrave in 1713. In this letter, Waldegrave provides a minimaxed mixed strategy solution to a two-person version of the card game La Hire. James Madison made what we now recognize as a game-theoretic analysis of the way states can be expected to behave under different systems of taxation. In his 1838 Recherches sur les principes mathématiques de l'art copyright des richesses, Antoine-Augustin Cournot considered a duopoly and presents a solution that is a restricted version of the Nash equilibrium. The Danish mathematician Zeuthen proved that the mathematical model had a winning strategy by using Brouwer's fixed-point theorem. In his 1938 book Applications au jeu d'hasard and earlier notes, a Permel-Mile-Bowrell proved a minimax theorem for two-person zero-sum matrix games only when the payoff matrix was symmetric. Bowrell conjectured that non-existence of mixed strategy equilibria in two-person zero-sum games would occur, a conjecture that was proved false. Game theory did not really exist as a unique field until John von Neumann published a paper in 1928. Von Neumann's original proof used Brouwer's fixed-point theorem on continuous mappings into compact convex sets, which became a standard method in game theory and mathematical economics. His paper was followed by his 1944 book Theory of Games and Economic Behavior. The second edition of this book provided an axiomatic theory of utility, which reincarnated Daniel Bernoulli's old theory of utility as an independent discipline. Von Neumann's work in game theory culminated in this 1944 book. This foundational work contains the method for finding mutually consistent solutions for two-person zero-sum games. During the following time period, work on game theory was primarily focused on cooperative game theory, which analyzes optimal strategies for groups of individuals, presuming that they can enforce agreements between them about proper strategies. In 1950, the first mathematical discussion of the prisoner's dilemma appeared, and an experiment was undertaken by notable mathematicians Merrill M. Flood and Melvin Sher, as part of the Rand Corporation's investigations into game theory. Rand pursued the studies because of possible applications to global nuclear strategy. Around this same time, John Nash developed a criterion for mutual consistency of players' strategies, known as Nash equilibrium, applicable to a wider variety of games than the criterion proposed by von Neumann and Morgenstern. This equilibrium is sufficiently general to allow for the analysis of non-cooperative games in addition to cooperative ones. Game theory experienced a flurry of activity in the 1950s, during which time the concepts of the core, the extensive form game, fictitious play, repeated games, and the Shapley value were developed. In addition, The first applications of game theory to philosophy and political science occurred during this time. In 1965, Reinhard Selten introduced his solution concept of subgame perfect equilibria, which further refined the Nash equilibrium. In 1967, John Harsanyi developed the concepts of complete information and Bayesian games. Nash, Selten and Harsanyi became economics Nobel laureates in 1994 for their contributions to economic game theory. In the 1970s, game theory was extensively applied in biology, largely as a result of the work of John Maynard Smith and his evolutionarily stable strategy. In addition, the concepts of correlated equilibrium, trembling hand perfection, and common knowledge were introduced and analyzed. In 2005, game theorists Thomas Schelling and Robert Oman followed Nash, Selten and Harsanyi as Nobel laureates. Schelling worked on dynamic models, early examples of evolutionary game theory. Oman contributed more to the equilibrium school, introducing an equilibrium coarsening, correlated equilibrium, and developing an extensive formal analysis of the assumption of common knowledge and of its consequences. In 2007, Leonid Hurwicz, together with Eric Marskin and Roger Myerson, was awarded the Nobel Prize in Economics for having laid the foundations of mechanism design theory. Myerson's contributions include the notion of proper equilibrium, and an important graduate text, Game Theory, Analysis of Conflict. Hurwicz introduced and formalized the concept of incentive compatibility. In 2012, Alvin E. Rath and Lloyd S. Shapley were awarded the Nobel Prize in Economics for the theory of stable allocations and the practice of market design. In popular culture, based on the book by Sylvia Nasser, the life story of game theorist and mathematician John Nash was turned into the biopic A Beautiful Mind starring Russell Crowe. Games theory and theory of games are mentioned in the military science fiction novel Starship Troopers by Robert A. Heinlein. In the 1997 film of the same name, the character Carl Jenkins refers to his assignment to military intelligence as to games and theory. One of the main gameplay decision-making mechanics of the video game Zero Escape, Virtue's last reward, is based on game theory. Some of the characters even reference the prisoner's dilemma. The film Doctor Strangelove satirizes game-theoretic ideas about deterrence theory. For example, nuclear deterrence depends on the threat to retaliate catastrophically if a nuclear attack is detected. A game theorist might argue that such threats can fail to be credible, in the sense that they can lead to subgame imperfect equilibria. The movie takes this idea one step further, with the Russians irrevocably committing to a catastrophic nuclear response without making the threat public. See also, AI effect, applications of artificial intelligence, chain store paradox, collective intentionality, combinatorial game theory, confrontation analysis, glossary of game theory, intra-household bargaining, Perrondo's paradox, quantum game theory, quantum refereed game, rationality, reverse game theory, self-confirming equilibrium, lists, list of emerging technologies, list of games in game theory, outline of artificial intelligence, notes. References and further reading, textbooks and general references, Oman, Robert J., Game Theory, The New Palgrave, A Dictionary of Economics 2, ppA 460-82a. The New Palgrave Dictionary of Economics. 2nd edition, Game Theory by Robert J. Oman. Abstract. Game Theory and Economics, Origins of, by Robert Leonard. Abstract. Behavioral Economics and Game Theory by Farrukh Gul. Abstract. Camera, Colin, Behavioral Game Theory, Experiments in Strategic Interaction, Russell Sage Foundation, ISBN A978-0-691-09039-9. A description and introduction, ppA 1 €25. Dirkzit, Avinash. Nalaboff, Barry, Game Theory, in David A. Henderson, Concise Encyclopedia of Economics, ISBN A978-08659766658. OCLCA 237794267 A. Dutta, Prijit K., Strategies and Games, Theory and Practice, MIT Press, ISBN A978-0-262-04169-0A. Suitable for undergraduate and business students. Fernandez, L.F. Brouwer, H.S., Game Theory with Economic Applications, Addison Wesley, ISBN A978-0-201-84758-1A. Suitable for upper-level undergraduates. Freudenberg, Drew. DeRolle, Jean, Game Theory, MIT Press, ISBN A978-0-262-06141-4A. Acclaimed reference text. Description. Gibbons, Robert D., Game Theory for Applied Economists, Princeton University Press, ISBN A978-0-691-00395-5A. Suitable for advanced undergraduates. Published in Europe as Robert Gibbons, A Primer in Game Theory, London, Harvester Wheatsheaf, ISBN A978-0-7450-1159-2A. Gintis, Herbert, Game Theory Evolving, A Problem-Centered Introduction to Modeling Strategic Behavior, Princeton University Press, ISBN A978-0-691-00943-8. Green, Jerry R. Maskaliel, Andrew. Winston, Michael D., Microeconomic Theory, Oxford University Press, ISBN A978-0-19-507340-9A. Presents game theory in formal way suitable for graduate level. Edited by Vincent F. Hendricks, Pell G. Hansen, Pell G. Hendricks, Vincent F., eds., Game Theory, 5 Questions, New York, London, Automatic Press/VIP, ISBN A977-87-991-013-4-4A. Snippets from interviews. Howard, Nigel, Paradoxes of Rationality, Games, Metagames, and Political Behavior, Cambridge, Massachusetts, The MIT Press, ISBN A978-0-262-58237-7A. Isaacs, Rufus, Differential Games, A Mathematical Theory with Applications to Warfare and Pursuit, Control and Optimization, New York, Dover Publications, ISBN A978-0-486-40682-4A. Jalmi, Christian, Introduction to Game Theory, Copenhagen, Book Buen, ISBN A978-87-403-0280-6A. Leighton Brown, Kevin. Schuang, Yoav, Essentials of Game Theory, A Concise, Multidisciplinary Introduction, San Rafael, California, Morgan and Claypool Publishers, ISBN A978-1-59829-593-1A. An 88-page mathematical introduction. Free online at many universities. Miller, James H., Game Theory at Work, How to Use Game Theory to Outthink and Outmaneuver Your Competition, New York, McGraw-Hill, ISBN A978-0-07-140020-6A. Suitable for a general audience. Meyerson, Roger B., Game Theory, Analysis of Conflict, Harvard University Press, ISBN A978-0-674-34116-6A. Osborne, Martin J., An Introduction to Game Theory, Oxford University Press, ISBN A978-0-19-512895-6A. Undergraduate Textbook. Paperino, Paul, Game Theory for Business, Probabilistic Publishing, ISBN A978-0-9647938-7-3A. Primer for Businessmen and Women. Petruian, Leon. Zienkiewicz, Nikolay, Game Theory, World Scientific Publishers, ISBN A978-981-02-2396-0. Osborne, Martin J. Rubinstein, Ariel, A Course in Game Theory, MIT Press, ISBN A978-0-262-65040-3A. A Modern Introduction at the Graduate Level. Poundstone, William, Prisoner's Dilemma, John von Neumann, Game Theory and the Puzzle of the Bomb, Anchor, ISBN A978-0-385-41580-4A. A General History of Game Theory and Game Theoreticians. Rasmussen, Eric, Games and Information, An Introduction to Game Theory, Wiley-Blackwell, ISBN A978-1-4051-3666-2. Schuang, Yoav. Leighton Brown, Kevin, Multigent Systems, Algorithmic, Game Theoretic, and Logical Foundations, New York, Cambridge University Press, ISBN A978-0-521-89943-7A. A Comprehensive Reference from a Computational Perspective. Downloadable free online. Williams, John Davis, The Complete Strategist, Being a Primer on the Theory of Games of Strategy, Santa Monica, Rand Corporation, ISBN A978-0-8330-4222-4. Appraised Primer and Popular Introduction for Everybody, Never Out of Print. Roger McCain's Game Theory, A Non-Technical Introduction to the Analysis of Strategy, Christopher Griffin Game Theory, Penn State Math 486 Lecture Notes, PPA 169, CC by NCSA License, Suitable Introduction for Undergraduates, Webb, James N., Game Theory, Decisions, Interaction and Evolution, Springer Undergraduate Mathematics Series, Springer, ISBN A1-84628-423-6. A consistent treatment of game types usually claimed by different applied fields, for example Markov decision processes. Joseph E. Harrington Games, Strategies, and Decision Making, Worth, ISBN 0-7167-6630-2. Textbooks suitable for undergraduates in applied fields. Numerous examples, fewer formalisms in concept presentation. Drew Freudenberg, David K. Levine, ed. A Long-Run Collaboration on Long-Run Games. Hackensack, New Jersey, World Scientific. PA 416. ISBN A978-981-281-846-1. Adam Brandenberger. The Language of Game Theory, Putting Epistemics into the Mathematics of Games. World Scientific Series in Economic Theory, Volume 5. Hackensack, New Jersey, World Scientific. PA 300. ISBN A978-981-4513-43-2. Roger A. McCain. Game Theory, A Non-Technical Introduction to the Analysis of Strategy. Hackensack, New Jersey, World Scientific. PA 600. ISBN A978-981-4578-87-5. Historically Important Texts, Oman, R.J. and Shapley, L.S., Values of Non-Atomic Games, Princeton University Press, Cornott, A. Augustin, Recherches sur les principles mathématiques de l'art. Copyright Henri Desrichesses, Libraire des Sciences Politiques et Sociales, Edgeworth, Francis Y., Mathematical Psychics, London, Kagan Paula, Farquharson, Robin, Theory of Voting, Blackwell, ISBN A0-631-12460-8. Luce, R. Duncan. Raver, Howard, Games and Decisions, Introduction and Critical Survey, New York, Wiley. Reprinted edition, R. Duncan Lucia. Howard Raver, Games and Decisions, Introduction and Critical Survey, New York, Dover Publications, ISBN A978-486-65943-5A. Maynard Smith, John, Evolution and the Theory of Games, Cambridge University Press. ISBN A978-0-521-28884-2. Maynard Smith, John. Price, George R., The Logic of Animal Conflict, Nature 246, 15 18, Bibcode, 1973 Nature 246. 15s, doi, 10.1038/246015 AO. Nash, John, Equilibrium Points in N-Person Games, Proceedings of the National Academy of Sciences of the United States of America 36, 48 Bibcode, 1950 PNAS. 36. 48N, doi, 10.1073/FNAS 36.1.48, PMCA 1063129, PMIDA 16588946. Shapley, L.S., A Value for N-Person Games, in Contributions to the Theory of Games Volume 2, H. W. Kuhn and A. W. Tucker, Shapley, L.S., Stochastic Games, Proceedings of National Academy of Science Volume 39, ppA 1095 1100. Von Neumann, John, Zur Theorie des Gesellschaftsspiels, Mathematische Annalen 100, pages 295 320. English translation, On the Theory of Games of Strategy, in A. W. Tucker and A. D. Luce, ed., Contributions to the Theory of Games, v. 4, pages 42. Princeton University Press. Von Neumann, John. Morgenstern, Oskar, Theory of Games and Economic Behavior, Princeton University Presse, Zermelo, Ernst, Aberrain Anwendung der Menschenlehre auf die Theorie des Schachspiels, Proceedings of the Fifth International Congress of Mathematicians 2, 501 €4. Other print references, Ben David, S. Borodin, Alon. Karp, Richard. Tardos, G. Wiederson, A. On the Power of Randomization in Online Algorithms, Algorithmica 11, 2 €14, doi, 10.1007/BF01294260. Bickery, Christina, Rationality and Coordination, Cambridge University Press, ISBN A0-521-57444-7. Downs, Anthony, An Economic Theory of Democracy, New York, Harper, Gautier, David, Morals by Agreement, Oxford University Press, ISBN A978-0-19-824992-4A. Alan Gibbard, Manipulation of Voting Schemes, A General Result, Econometrica, Volume 41, No. 4, ppA 587 €601. Grimm, Patrick. Kokalis, Trina. Ali Tafti, Ali. Kilb, Nicholas. St. Denis, Paul, Making Meaning Happen, Journal of Experimental and Theoretical Artificial Intelligence 16, 209 €243, doi, 10.1080/09528130412331294715. Harper, David. Maynard Smith, John, Animal Signals, Oxford University Press, ISBN A978-0-19-852685-8. Harsanit, John C., An Equilibrium Point Interpretation of Stable Sets, Management Science 20, 1472 €1495, doi, 10.1287/MNSC. 20.11.1472. Levy, Gilat. Raisin, Ronnie, It Takes Two, An Explanation of the Democratic Peace, Working Paper, Lewis, David, Convention, A Philosophical Study, ISBN 978-0-631-23257-5. MacDonald, John, Strategy in Poker, Business and War, W. W. Norton, ISBN A0-393-31457 Zam. A Layman's Introduction. Quine, W. V. O., Truth by Convention, Philosophical Essays for A. N. Whitehead, Russell and Russell Publishers, ISBN A978-0-8462-0. 0970-6, Quine, WVO, Carnap and Logical Truth, Synthese 12, 350 Euro 374, doi, 10.1007/BF00485423, Mark A. Satterthwaite, Strategy Proofness and Arrows Conditions, Existence and Correspondence Theorems for Voting Procedures and Social Welfare Functions, Journal of Economic Theory 10, 187 Euro 217. Siegfried, Tom, A Beautiful Math, Joseph Henry Press, ISBN A0-309-10192-1, Skimes, Brian, The Dynamics of Rational Deliberation, Harvard University Press, ISBN A0-674-21885 Zan, Skimes, Brian, Evolution of the Social Contract, Cambridge University Press, ISBN A978-0-521-55583-8, Skimes, Brian, The Stag Hunt and the Evolution of Social Structure, Cambridge University Press, ISBN A978-0-521-53392-8, Sober, Elliot. Wilson, David Sloan, Unto Others, The Evolution and Psychology of Unselfish Behavior, Harvard University Press, ISBN A978-0-674-93047-6, Thrall, Robert M. Lucas, William F., Person Games and Partition Function Form, Naval Research Logistics Quarterly 10, 281 Euro 298, doi, 10.1002/nav 3,800,100,126, Dolov, Shlomi. Panagopoulou, Panagita. Raby, Michael. Schiller, Elad Michael. Spirakis, Paul, Rationality Authority for Provable Rational Behavior, ACMPODC, 289 Euro 290, doi, 10.1145/1,993,806.1993858. Websites, Haswinkel, Michiel, ed., Games, Theory of, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-Fora, Paul Walker, History of Game Theory page. David Levine, Game Theory. Papers, lecture notes and much more stuff. Alvin Roth, Game Theory and Experimental Economics page. A Euro comprehensive list of links to game theory information on the web. Adam Kallai, Game Theory and Computer Science. A Euro lecture notes on game theory and computer science. Mike Schott, GameTheory.net. A Euro lecture notes, interactive illustrations and other information. Jim Ratliff's graduate course in Game Theory. Don Ross, Review of Game Theory in the Stanford Encyclopedia of Philosophy. Bruno Verbeek and Christopher Morris, Game Theory and Ethics. Elmer G. Yanes, Game Theory. A Euro Introduction, Worked Examples, Play Online 2-Person Zero-Sum Games. Menachem Kaminsky, Game Theory and Politics. A Euro Syllabuses and Lecture Notes for Game Theory and Political Science. Websites on Game Theory and Social Interactions. Kesson Green's Conflict Forecasting. A Euro C papers for evidence on the accuracy of forecasts from game theory and other methods. McKelvey, Richard D., McLennan, Andrew M., and Chirossi, Theodore L. Gambit, Software Tools for Game Theory. Benjamin Polak, Open Course on Game Theory at Yale. Videos of the course, Benjamin Moritz, Bernhard Carr. Paragraph NSGEN, Danny Bez, Ronnie Weish, Spill Theory Software DA, an application for game theory implemented in Java. Antonin Kusera, Stochastic Two-Player Games.